Okay, in this video, we're going to once again talk about translations, and this time it's going to be translations of geometric functions. And we see here some parent functions. We're not necessarily parent functions, but some general functions of our three trig, basic trig functions. Like other functions, trigonometric functions can be translated. Given the functions to the left that I just showed you, h, and you see the h in here, h is going to be a vertical shift, or excuse me, a horizontal shift because it's on that x value. So is a horizontal, and k is going to represent a vertical shift as it has with our other functions. If you have a positive k, that's going to shift your graph up, and a minus k is going to shift it down. If you have a plus h, remember that this works backwards. Plus is going to shift it left, and a minus is going to shift it right. So therefore, we're going to describe first off the translations. So notice here that this is not the cosine of x plus 2. This is not in parentheses, and unless there's parentheses there, never assume that you're finding the cosine of two different things. We're simply finding the cosine of x, and then we have the plus 2 outside parentheses. It's not inside with the x value, so therefore we have a vertical translation up 2 units. Same way with the second one. This minus 1 here is not inside with the x, so something's going to happen vertically. Since it's a minus, we're going to shift it down, and we're going to shift it down 1 unit. Now, on the next ones, we have a plus inside parentheses with that x value. It does work backwards from the way you would think. That plus pi over 2 is going to move it left pi over 2 radians, or left 90 degrees. And a minus inside here with that x value is going to shift your graph right, and it's going to shift it right pi units, or right 180 degrees. Pi if you're graphing in radians, 180 if you're graphing in degrees. Now a midline. Now and I kind of touched on this as we were graphing in the last section, the midline is that middle of the graph. It's kind of like if this was an actual ocean wave. If the waves quit going, okay, where does it level out to? So here would be the middle line, or the midline. Now notice here in this one, that midline got shifted up actually 4 units. This is a sine of x plus 4. So when you add 4 to it, it's going to shift your entire graph up, including that middle line. So shifting a graph vertically will create a new horizontal axis called the midline. And again, I did mark those midlines for each of the graphs over there. This is the reference line in which a graph oscillates. The equation of the midline is y equals k, to where normally it's y equals 0 for a normal sine or cosine curve. However, if you shift it, you put a plus or minus on the end of your graph, it's going to move it up or down that many units. Okay, let's look at some graphs of these. Number 5 says graph the function, then identify the characteristics. So I'm going to go ahead and look at all the different transformations here. Now for a normal sine curve, you have an amplitude of 1 and a period of 2 pi. However, I do want to talk transformations here. Anytime that you multiply a function by 3/2, again, this is a vertical stretch. Anytime you stretch it vertically times a factor, it's going to change that amplitude. So therefore, when you take that 1 and you multiply it vertically times a factor of 3/2, that's going to change your amplitude to a value of 3/2. And we talked about that last section. And I do want to remind you that if you take and you multiply your x value something, that'd be a horizontal stretch or compression, that would actually change the period. However, this one has not been changed, so therefore the period is still going to be 2 pi. The phase shift is how far left and right. We call it a phase shift, but a phase shift is simply a horizontal translation. That's all that means. This one has no horizontal translation. Again, you can look at the x value. Nothing has happened. So on phase shift, we are going to put none. Vertical shift, there is one. We're going to shift everything up 3 units. So therefore, shifting up 3, which is going to move that midline from y equals 0 to y equals 3. So if you want to, you can think of, again, this horizontal line right here. That's going to be the middle of your sine curve. Now let's look at, let's plot some points on this graph and see what it would look like. Now notice what I've done here. This sine curve is going to go through a complete cycle every 2 pi units. So I put a dot here because I know that if I plug in 0, I get 3. And that same point is going to repeat 2 pi units down the road and down this way 2 pi units as well. So we're going to have a complete cycle which looks like this between here and here. So I know that halfway through, we can do this just to kind of cheat the way we're going to graph this. Halfway through, we know that this thing is going to cross the x-axis again, so we can put a dot at pi and negative pi. And then the next thing is just knowing, okay, does my graph from this dot, does it increase or does it decrease? And the way that we can do that is we can use Desmos, or we can just plug in a point halfway between 0 and pi, which would be like pi over 2. So when I plug in my pi over 2, I get the sine of pi over 2, or the sine of 90, is going to equal 1. 3 halves times 1 is 3 halves. And then when I add 3 to that, that gives me 3 halves plus 6 halves, which is 9 halves. So 9 halves, that's going to be 4.5. So that's going to be right in there. So that kind of gives me the general shape of my graph. And it also, you can see that amplitude there. We have an amplitude of 3 halves. So I know that my graph is going to go uphill, and then it's going to come back down. And then I know it continues downhill. And halfway through those 2 points, we can apply that same amplitude. And I know that my graph is going to look something like that. And it's going to repeat and do the exact same thing on the other side. It's going to finish that same cyclic looking formation. So we have here then a picture of what this graph would look like. And you can see the phase shift, the vertical shift, you can see all those things being applied. Okay, the next one, amplitude. I'm going to put not applicable because since it's a tangent graph, you don't have amplitude for tangent graphs. The period of this thing, since it is tangent, a normal period for tangent is pi, and this one has not been stretched or compressed any horizontally, so our period is still going to be pi. Our phase shift is right here. It's how far right or left my graph is shifted. So we're going to shift this thing, since it's a plus, that's going to move it left pi over 2 units. Our vertical shift, if there is a plus or a minus out here, it's going to move it up or down. This one has none. And the midline, therefore, has not changed. So we have a midline at y equals 0, which would be your x-axis. So pretty much this is your normal tangent graph that has been shifted left pi over 2 units. Now let's talk about our asymptote lines here. Now normally for a tangent graph, the tangent of 90 is undefined, the tangent of 270 is undefined. So normally I would have an asymptote line here at 90 degrees. However, since I'm shifting my graph left 90 degrees, I will have now a new asymptote line here at x equals 0. Normally at 270 is another one. However, when I shift it to the left 90 degrees, I have one at pi. So I'll have one at 0 pi. I'll have another asymptote line at 2 pi. And if you don't understand that, you can plug in any of these values, and you'll see that any of these would give you an undefined value at as you plug them in. So there's your asymptote lines. And from there, we kind of know the general shape of a tangent function. This one's not been shifted up, down, up or down, either one. So therefore, we have kind of the general shape would look something like this, to where we're going to start at the midline, and we're going to increase to the right and simply decrease to the left. And we can do that a few times, and that's going to be what our tangent function looks like. Let's do one more right here. And again, the reason we do it over and over is because this is a cyclic function. It repeats again and again. Number 7. You have all your different transformations here, and there are several. So again, since it's a cosine curve, and this is the same for sine and cosine, normally you have an amplitude of 1 and you have a period of 2 pi, and that's something we need to remember. However, this one has been changed. Our amplitude has been stretched, and the way that we're going to stretch our amplitude is by applying a vertical stretch. And this is going to be 4 times taller than what it normally is. So therefore my amplitude is now not 1, but it is 4 times greater. It's going to be 4. Our period, what's going to change the period is any multiplication or division. that's applied directly to our x value. So if you notice inside of here, where our x value is located, this minus pi is going to shift it right. That doesn't change your period. What's going to change it is when you stretch or compress it. So if there's a 2/3 being multiplied by your x stuff, that's going to take and it's going to stretch or compress your period by a factor of the reciprocal of 2/3. So we're going to do times 3/2, which is what we did last section. When we apply this transformation by multiplying by 3/2, we find out the 2's are going to cancel and it gives me 3 pi. So instead of having a period of 2 pi, we now have a period of 3 pi. So our amplitude again is now 4. Our period is 3 pi. Our phase shift is this minus pi, which is going to move it right pi units. A vertical shift is applied here at the end. That's going to move it up 1 unit. So therefore, our midline is now going to be, instead of y equals 0, it is now going to be y equals 1. So I'm going to draw this midline, which is going to be about right there. And then let's take some points that are on our graph and let's plot this thing. Now, one easy point to plot, when I plug pi in, I notice when I do pi minus pi, I get 0. When I do 2/3 times that, it's still 0. So you have inside of parentheses here the cosine of 0, which we know is 1. And if you do 4 times 1 plus 1, that'll be 4 plus 1, which is 5. So when I plug in pi, I get 5. And I know for a fact that that's going to be one of my highest points on my graph. And the reason for that is I have an amplitude of 4. So therefore, here's my midline. And the distance from my midline to the top of my graph there is 4. So that must be one of the highest points. We also know that that point is going to reoccur every 3 pi units. So since that occurred at 1 pi, we can actually go back over here at -2 pi, and we know it's going to occur again there. Another thing that we can do is we know that between those two maximum points, because of the symmetry of a sine or cosine curve, we know that we're going to have a minimum point directly in between those. So you could actually count boxes over or whatever you'd like to do, but it's going to be right here. So we could actually go back to our midline and go down 1, 2, 3, 4, and we're going to have a minimum point on our function there. And again, that minimum point is going to occur every 3 pi units. So if we could go over 3 pi from there, which I don't think we can, you can actually count boxes there. I think it's 1, 2, 3, 4, 5, 6 boxes over. 1, 2, 3, 4, 5. You just barely run out of room. So there's another minimum point. And that's just, again, that's one tip that you can use to actually graph these. And then you could, just to sketch this graph out, you can just simply go down, come back up from there, then go back down, because we know the general shape of what these things will look like. So this graph is going to look something like that. Okay, the next one, we have another tangent graph. And again, a tangent does not have an amplitude. The normal period of a tangent function is going to be pi. However, if you notice inside here, and I don't like the fact that they don't put brackets around that, they put the parentheses around x plus pi over 4, but that whole thing is inside with your x, the 2 and the pi over 4. So therefore, this 2 right here is going to change that, is going to change that period. It's going to change it by a factor of the reciprocal. So that's going to multiply your x values. That's going to multiply your horizontal values by a factor of 1/2. So we're going to take our old period, we're going to multiply it by 1/2, and we're actually going to have a new period of pi over 2. Our phase shift is whatever's being added or subtracted to the x, so that would move it a left pi over 4. A vertical shift would be a -3, would be a down 3 shift. So therefore, our midline, which is normally at y equals 0, will now be at y equals -3. So we can kind of, again, once we draw this midline, we can kind of use it as our x-axis used to be. That's going to be kind of our new x-axis as we're graphing this. So that's going to be the middle of our graph vertically. Now, I do want to remind you something about the asymptote lines that we talked about last section. The asymptote lines for a tangent function are located at the odd values of pi over 2 times the absolute value of b. So if you want to use that fact, you got to be a little bit careful with these because this would be pi over 4. So those values will be located at 1 pi over 4, 3 pi over 4, 5 pi over 4, and so on and so forth. But there's an issue. All of these values have been moved left pi over 4. So instead of pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4, which is like it normally would be, if we move all those left pi over 4, we get 0. Instead of 3 pi over 4, it'd be 2 pi over 4, which is be pi over 2. Instead of 5 pi over 4, it would be 4 pi over 4, because again, we're moving it left pi over 4. 4 pi over 4 would be pi, and then so on and so forth. So we actually have asymptote lines at 0, pi over 2, which would be located right here, pi, which is located right here, and then every pi over 2 units after that. So here is all the asymptote lines for this graph. And we could actually, once we have those asymptote lines, we can very easily just sketch out what this graph would look like. You can plug in some points if you'd like to, but this has not been flipped. So therefore, we know that we can go to our midline, and we can kind of just follow those asymptote lines up and down, and that our tangent curve will look something like this. And let me pause it. Well, try that again. Let me pause it and go ahead and finish this out. And here's what your graph would look like. Okay, next up we have the function y equals 3 times the sine of, and again, I like brackets around this, 4 parentheses x minus pi over 2 minus 2. So again, we can go through all those amplitude periods and all this over here. Normally your amplitude is 1 for a sine curve. However, this is stretched at 3 times as tall, so therefore now our amplitude will be 3. The period for a sine curve is normally 2 pi. However, this is going to transform it. We're going to take our 2 pi and we're actually going to multiply it by the reciprocal of 4, which will be 1/4. Or you can use the formula we talked about last section. Reduce that, that'll be a 1 and 2, gives you an amplitude of pi over 2. Or excuse me, a period of pi over 2, which means your graph is going to repeat every pi over 2 units. We have a phase shift right here. That's going to move it right pi over 2 units from where it normally is. We have a vertical shift here that will move it down 2 units. So therefore, our midline for this graph will now be at y equals -2. Let me go ahead and sketch that midline, which is going to be about right here. So that's going to be the middle of our sine curve. Let's plug in some points, maybe like you can plug in like a pi over 2 very easily to give you a 0 in here to kind of get a point on that graph. If I were to plug in a pi over 2, I would get pi over 2 minus pi over 2, which is 0. 4 times 0 is 0. The sine of 0 is 0. 3 times 0 is 0. Subtract 2, it gives you -2. So when I plug in pi over 2, I get -2. And again, I know that that value is going to repeat every pi over 2 units. So therefore, since it occurs here, then I can go over pi over 2 and I can put another one. Let me do a different color here. So I have a point here, a point here, a point here, and a point here. Now, that is a complete cycle. So let's think about that. Since it has to go through a complete cycle from here to here, it's got to go down or up and then back down. So I know that since that's a complete cycle, it's going to have to cross again in between those two values. So I'm going to have an x-intercept everywhere between these values as well. So I'm going to have another point on my graph, all of these places. So pretty much every pi over 4, I'm going to have an x-intercept on this graph. Now the next question is, what happens in between these values? Does my graph increase? Does my graph decrease? So what we could actually do is plug in, since this is 0 and this is pi over 4, I could plug in maybe a pi over 8 or something like that. Or if we know the general shape, I know that my graph normally at 0, it goes up, comes back down, and then goes back up again. However, this thing has been shifted right pi over 2. So that moved your whole starting point over from 0 to here. So it's going to go through a complete cycle starting here. Your amplitude as well. We can apply that. This is going to be a fairly a little bit taller graph. So instead of just going up a single box, I'm going to have to go up 3 boxes. So therefore, again, we can plug in like a pi over 8 or something to see what's going to happen between these dots. You can look at Desmos, different options that you have here. And as I go through any of these processes, as I plug in pi over 8, I notice I get a value of 1 there when I plug it in. So that's honestly all the points that I'm going to need for my graph, because I know if my function starts here, goes up, comes back down, I know that it's going to have to continue going down and it will have the same amplitude. So it's going to continue this exact same process, and it's going to look something like this. And I know that this value here is going to again occur every pi over 2 units. So we could actually go ahead and put those values on our graph. This lowest value is going to occur every pi over 2 units as well, which in this case is going to be over about a couple of boxes. So we can put those dots there and continue that same pattern. And here's what your graph's going to look like. And you can see that it does fit all those characteristics. Number 10, we have yet another cosine graph. Here is all my transformations that's going to occur. Let's first start out with the amplitude, which is out front. The amplitude will not change because there's no number that's vertically stretching it. My period will change, and here's how it's going to change. Normally, you have a period of 2 pi for a cosine curve. However, we're going to multiply by the reciprocal of this 2. 2's cancel, and we will now have a period of pi units. We have a phase shift here. That's going to shift it left 3 pi over 4, which is 135 degrees. We have a vertical shift that's going to move it right here up 4 units. So therefore, we have now a midline at y equals 4. And you can sketch that midline if it helps. That's kind of like your new x-axis that you're going to use. And it's going to go up and down from there. And it's going to go up and down this much. That's going to be how far it is to the maximum and how far it is to the minimum. So pretty much if we can get now a point on our graph, then we can find several more values. Again, I like to plug in the opposite of this. If you plug in negative 3 pi over 4, when you plug that in, this value here goes to 0. 2 times 0 is 0, and you now have the cosine of 0. Cosine of 0 we know is 1. When you add 4 to that, it gives you 5. So when you plug in negative 3 pi over 4, which is located 1, 2, 3 right here, you get a value of 5, which is here. So let me use that right there. Okay. We know that point is going to reoccur every pi units. So we can actually go over pi units from there. And in our graph, pi units is 4 boxes. So 1, 2, 3, 4 boxes. So that maximum value is going to occur every 4 boxes. 1, 2, 3, 4. 1, 2, 3, 4. So that's going to be all of our all of our maximums on our graph. We know that we're going to have a minimum value with the same amplitude that's going to occur in between those maximum values. So you could actually come down here and you could put a minimum value on your graph as well. So you kind of already see a picture of what this graph's going to look like. Between that minimum and maximum, it's going to cross the x-axis in all of these places. And once we go through and we connect all of our dots, here's what our graph looks like. And you can see the amplitude of 1 there, the period of pi units, the phase shift left 3 pi over 4. You can see all those values. Okay, one more, number 11. Again, we have a tangent function. Let's go through the amplitude. There is not an amplitude for the tangent function. A period, normally the period is going to be pi. However, if there's a value inside this bracket with the x's, which is right here, it's going to stretch that period by a factor of the reciprocal of that. So we're going to multiply our previous period by 2, and we're now going to have a period of 2 pi. Our phase shift is located right here. That moves our original graph, our original parent function of y equals tan x left pi. We're going to have a vertical shift that's going to move it up 1. So therefore, we're going to have a midline at y equals 1. So I like to go ahead and draw that midline. And then let's plot some points so that we can see what our graph's going to look like. Again, we could very easily plug in a value like, let me go back up to the original, plug in a value like negative pi right here to get a point on our graph. If you plug in negative pi, this goes to 0, which means all this goes to 0. So you have the tangent of 0, which is 0. 2 times 0 is 0, plus 1 is 1. So at negative pi, you have a value of 1. which would be kind of like an x-intercept. However, your graph has been moved up 1 unit. Now again, that value is going to repeat every 2 pi units. So it could go to the right 2 pi units, and it's going to look something like that. Now here's the difference with your tangent graph. With a tangent graph, you're going to have between those 2 points where you cross the midline, you're actually going to have an asymptote line. So you could actually draw your asymptote line there. You could draw another asymptote line every 2 pi units. So here is going to be the asymptote lines for this graph. And then once you have an asymptote line for a tangent graph, we know that it just kind of follows that asymptote line. So it's going to look something like this. So we're going to follow it here. Then we're going to go down to the other side. And that again is going to repeat every 2 pi units. So there's your graph of your tangent curve.